Thank you very much. And thanks to you for all your interest. Thanks to Lexi and the department for all of the organizations. I'm really pleased to be here. A dead tree in Africa was the first sign of climate change that I saw in the field. It was a tree called Yir in Wolof. Prosopis africana is the scientific name. And normally, it has a verdant green crown, but this tree was gray and lifeless. But it didn't have any axe marks or insect tracks or signs of its mortality, except for being dry and lifeless and being in the Sahel. The Sahel is a savanna south of the Sahara Desert. It stretches across Africa, and it is characterized by arid zone trees, maybe 4 to 5 per hectare, very sparse. And that part of the world has experienced the most severe decline in rainfall in the global weather station record, 50% decline in a half century, and significant increase in temperature. Well, this tree was gray and lifeless, and it was in this cemetery of other dead trees, and people there depend on trees for their livelihoods, for the poles for huts, for firewood, for making live fences. Well, eventually I hiked 1,900 kilometers in the Sahel, counted thousands of trees, spoke in semi-structured interviews with hundreds of village elders, and then came back to Berkeley, went back to Berkeley and counted thousands of dots on historic aerial photos. And all of those analyses showed that 1 out of every 3 tree species had disappeared locally in a half century. 1 out of every species. And 1 out of every 5 adult trees had died in a half century. And so I conducted an attribution analysis. I analyzed 215 different environmental and socioeconomic variables. So environmental, temperature, precipitation, depth of water table, socioeconomic, population density, distance to road, distance to market, livestock densities. And the multivariate statistical analyses showed that 2 variables explained most of the death of the trees and disappearance of the tree species: temperature and precipitation. Increasing heat and increasing aridity had killed those trees, and previous research had attributed the drought and the increasing temperature to anthropogenic climate change. So carbon pollution from cars, coal burning, and other human activities half a world away had killed those trees in Africa. Well, from those dead trees in Africa to wildfire burning above natural levels in Yosemite, anthropogenic climate change has been damaging ecosystems around the world. Yet recent progress on cutting carbon pollution, cutting greenhouse gas emissions, and increasing sustainability offers hope for the future. So I'm going to talk about those issues on climate change and ecosystems and biodiversity in these 5 sections today. And a lot of what I'll discuss with you, review with you, are the findings of the Intergovernmental Panel on Climate Change, as you heard in the introduction. And the IPCC is the international science panel that produces the authoritative assessments of climate change and greenhouse gases, for which it was awarded a share of the 2007 Nobel Peace Prize. And there we are. This is the author group from the last report. and our assessment was published in 2022. And so I'm going to actually show you a lot of the results on ecosystems and biodiversity, and then more recent results on ecosystems and biodiversity. Starting with the human cause of climate change, which is important because it points us to the solution. So cars, coal burning, deforestation, and other human sources pump 11 billion tons of carbon into the atmosphere every year. But forests, soils, and oceans only naturally remove 5 billion tons. So the remainder, 6 billion tons, goes up in the atmosphere, and it's that fundamental imbalance that causes climate change. This graph shows global average surface temperature going back 3 million years. So this is the present going back 3 million years. And this is the concentration of carbon dioxide, the main greenhouse gas in the atmosphere, from 0 to above 400 parts per million. And we see that carbon dioxide varies a lot in geologic time. But this straight line right here is all of human history from the Industrial Revolution to today. And you see that, that human activities have pushed carbon dioxide way above its natural range of variation in the most recent period. Consequently, this has increased global surface temperature to its highest level in 120,000 years. And we have another straight line here. That's all of human history from the Industrial Revolution to today. So the global average surface temperature is now 1.2 degrees Celsius. If we look at the last decade, the last year, the annual average was regrettably the first year where temperature hit 1.5 degrees above pre-industrial levels. Pre-industrial levels here are 1850 to 1900. We prefer to use the decade because it evens out the interannual variation. Nevertheless, obviously, this is a substantial increase of global temperature. So this graph is an attribution analysis. This bar is the observed heating from thermometer measurements, from weather station measurements around the world. And then these bars are all potential contributing factors. Greenhouse gases, other human drivers, and then the natural sources. And what we see here is that the net human influence is exactly equal to the observed heating from weather station measurements, and that natural sources are negligible. So more than 99% of the observed heating is from human sources. Humans are causing climate change. All credible scientists agree on that fact. Climate change is like an increase of energy into the atmospheric system. It's the equivalent of burning one of those old incandescent light bulbs, a 100-watt light bulb, one of those over every square meter on Earth, day and night, 366 days a year, continuously. So that's a lot of heat. And so the major impact, of course, of that is the heating, the increase in average annual temperature. This map shows the change since pre-industrial, and the darkest reds here are 3.6 degrees Celsius above pre-industrial. So that's about 7 degrees Fahrenheit. The average is 1.2, but it, of course, exhibits a lot of spatial variation, particularly the high latitudes are heating up more, and it's hard to see at this spatial resolution, but also high elevations, mountain areas are heating up more. And that's because the atmosphere is thinner in both of those zones, and it's easier to heat up the thinner atmosphere. And also, the melting of the snow cover reduces the albedo, reduces the reflectance, and so more of the incoming radiation is absorbed. Anyway, we see just a few spots here, and they're not statistically significant, but just a few spots in the world that actually have not experienced heating. And one of them is in the southeastern United States, but it's not statistically significant. However, they haven't experienced the heating as much as we have here in the western United States. Zooming in here, colleagues and I analyzed for the first time the magnitude and patterns of climate change across the United States at 800-meter spatial resolution. And then for all of the national parks, now 433 national parks, the darkest reds here are 2.7 degrees per century. That's about 5 degrees per century. And our research revealed that human-caused climate change has heated the national parks at more than twice the rate of the country as a whole. Here's the rate in the national park system, and here's the rate for the United States as a whole. That's the 50 states and overseas territories. We'll zoom into Utah. This is the updated data for Zion National Park. So this is the analysis for Zion National Park as a whole. This is annual average temperature. And again, you see a lot of interannual variation. It hops up and down, but we see this slow march, statistically significant march upward from pre-industrial to today. That's 2024 right there, Zion National Park. This global map is like the previous global map, except it's for total annual precipitation, rainfall, and snowfall. And the darkest blues are a doubling of precipitation, and the darkest browns are actually a near elimination of precipitation. And climate change being this input into the atmospheric system, the energy expresses itself as more convection, and so generally more storms. And so the general tendency is to increase precipitation. So you actually see more blue here than brown over land. But climate change, it redistributes the energy and the moisture in idiosyncratic ways. And so it robs moisture from some areas, as I had been, as I told you in the introduction about the West African Sahel. And also we'll see here later in the southwestern United States. So some places have experienced an increase in rainfall, and some have experienced an extreme decline in rainfall. Zooming in on the United States, we actually see the southwestern drought here more in more close-up intensely. And here again, climate change has exposed the national parks disproportionately to aridity. This is the fraction of the area that experienced a statistically significant decline in rainfall. And you can see 12% park surface area versus 4% of the US. So human-caused climate change is disproportionately exposing our US national parks to increased heat and increased aridity. And why is that? Why would that be? Does anybody have an idea? You can actually see all the national parks in green. We'll just try to do this really quickly. Yes? Yes, that's one, higher elevation and higher latitude, yes. So you see actually 60% of the national park system is actually in Alaska. So, national parks are not a random sample. We've conserved the most remarkable ecosystems in the United States. They just happen to be in extreme environments. Okay, I'm going to show you now a series of ecological impacts. And the research has gone through these two scientific procedures, detection and attribution. Detection is finding a statistically significant difference, statistically significantly different from natural variation. And then attribution is examining the potential causes and determining that anthropogenic climate change dominates other non-climate change factors. A lot of methods for this. We don't have time. Tomorrow I'll talk in the next seminar about some of the attribution for wildfire. But anyway, all of the examples have gone through these. We can say anthropogenic climate change has caused these impacts. And most sadly, for nature, is the extinction of two animal species. One of them, the golden toad in Monteverde cloud forest in Costa Rica, where climate change has lifted the cloud deck and allowed the chytrid fungus to infect the amphibians. Regrettably, since 1989, this species has not been seen. Other amphibians are also suspected of extinction. The other species climate change has driven to extinction is the bramble K. malomies, a rodent on an island off the coast of Papua New Guinea that's part of Australia. And regrettably, sea level rise, the combination of sea level rise and storm surge has allowed storms to wash completely over the last island habitat of the species. And so it kills vegetation, and it potentially carried the little animals out to sea, regrettably gone extinct. Muir Glacier, Glacier Bay National Park in Alaska, 1941. Keep your eye on the top of the glacier against the mountain. 63 years later, glacier is gone from its lower reaches, 1941, and 63 years later. So at its lower reaches, Muir Glacier has lost over 640 meters of ice. That's greater in height than One World Trade Center in New York City. And this is one of over 172,000 glaciers around the world that are part of this glacier inventory, upon which glaciologists have determined that glaciers globally have lost about 1/5 of their mass since pre-industrial. 1/2 of that is due to anthropogenic climate change. In Bandelier National Monument and across the southwestern United States, including Utah, anthropogenic climate change has caused a drought since 2000. That's the most severe since the 1500s. And climate change has also intensified the heat that drives wildfire, including here in the eastern reaches of Tahoe National Forest, this astounding fire tornado in 2020. So climate change has lengthened the potential fire season in some places up to 2 months, and that includes some places in California. So wildfire is natural in many temperate zone ecosystems. It facilitates germination of certain pine species. It clears out the understory. But climate change is causing wildfire above those natural levels, including here in the rim fire that burned in California and up into Yosemite National Park, climate change has doubled the area burned by wildfire over natural levels since 1984. So we see here, these are the wildfires without climate change, and the orange is the additional surface area burned by caused by anthropogenic climate change. So this map actually summarizes the attribution of wildfire around the world, and I'll discuss this more tomorrow. But 4 areas now have experienced wildfire where climate change has increased it above natural levels, and we see Western North America, Southern South America, Southern Australia, and Central Asia. The Amazon, climate change has combined with deforestation to actually cause this part of the Amazon rainforest to become a net emitter of carbon, where it had previously been a net sink of carbon. So now more is being lost to wildfires than is being absorbed naturally through photosynthesis. Colleagues and I analyzed for the first time wildfire across, I'm sorry, ecosystem carbon across the state of California. And actually we uncovered that same result for California, that California ecosystems had become a net emitter of carbon. And a lot of this is because the 6% of the land that burned during that time period emitted 2/3 of the carbon from ecosystems. So we see actually fire perimeters all up and down, and then smaller fires in the Sierra Nevada. And that was much more than growth could add. Here in Rocky Mountain National Park and across the western United States, climate change has doubled tree mortality from drought, from wildfire, and from bark beetles. And bark beetles are also natural, but climate change is allowing them more and more to survive the winter and to move up in elevation and farther north than they had naturally been. So I told you this is just a summary of the data in my introduction, and we see tree species richness falling, trees per hectare falling, temperature going up, precipitation going down. I talked to you about the original research that I conducted in Senegal in West Africa, and then with colleagues we extended it across all of the Sahel. And then just earlier this year, a large group of colleagues and we actually looked at the lack of regeneration even farther south. So this has been an area of research of mine, tree mortality. But also, I should have mentioned in the introduction that one of the uses of the data was to show international development agencies that were working in Senegal at the time the potential for natural regeneration. You don't you see a few shrubs here, but actually kind of hidden here are a lot of native species that have germinated, and they're only about this tall, but livestock eat them, and straight row agriculture removes them. Anyway, I used this data to help convince international development projects to, rather than trying to plant trees and ask people to water them with extremely low survival rates, to rejuvenate this traditional practice of natural regeneration, which a lot of the fields actually doubled or tripled their tree densities. Okay, So back to the bad news. There was a little bit of good news in there, right? And we'll come back to good news, but we have to face and realize a lot of the patterns of the negative impacts first. In addition to the tree mortality, I was looking at biomes and the shifting of biomes. Biomes are major vegetation formations. They're the highest level of ecological organization, and depending on the classification, the world has 10 to 13 biomes. 3 of them here are savanna grassland, so the Sahel, and then deciduous woodland, the Sudan, where the trees gather into little groves, and then closed canopy forest here in Guinea. And that's caused by these gradients of increasing precipitation, decreasing temperature, so increasing vegetation productivity, and those differentiate the vegetation into these latitudinal biomes. And my research showed that anthropogenic climate change was shifting those biomes. This is about 1945. And the top is the Sahel biome. And the darker it is, the more arid zone species you have. So dark is arid. This is the Guinean biome. And the darker it is, the more green you have, the moister it is. So this is before, and this is 50 years later. So before and after. And so you can see that the arid species, this migration from the north, and then the moist zone species pulling back to the south. It was approximately 25 to 35 kilometers in a half century. That's a biome shift latitudinally. This is the eastern side of the Sierra Nevada, and it's an excellent illustration of elevation differentiating vegetation into biomes. And so we start with temperate shrubland, and then temperate bodley forest, so a lot of foothill oaks, and then temperate conifer forest, so a lot of pines, ponderosa pine, Jeffrey pine, and then kind of analogous to boreal conifer forest. So that's abies, fir trees, kind of colder zone trees. And then way at the top, alpine grassland. And then, of course, then there's sheer rock. This is, of course, the tallest point in the lower 48. And let's see, I hiked from here up to there. It's a great hike if you're ever able to do it. So these are elevation biomes, and research in Yosemite National Park has shown an upslope shift of the subalpine forest into formerly treeless meadows. You can see all of this right here. And that's in an area that has experienced heating at greater than the global average rate. So colleagues and I analyzed the risks of this under climate change. This is the, no, that's actually in the next section. But here I've actually compiled the cases. I compiled the cases for IPCC of biome shifts attributed to anthropogenic climate change around the world. And so we see in boreal, temperate, and tropical ecosystems, these biome shifts around the world, many in North America, as you see, but widespread around the world in places where ecologists have actually looked. It's possible it's occurred in many other places, but these are the places documented with published research of time series. Okay. Climate change has caused the local disappearance, the extirpation of populations of over 400 species, including the mountain ringlet in England. Another example of this is the black-throated sparrow and many other arid zone bird species in Mojave National Preserve, Joshua Tree National Park, and Death Valley National Park in Southern California. My colleagues at UC Berkeley have published this research on the loss of bird species in the Mojave Desert ecosystem protected areas. This is a tropical rainforest in Costa Rica, and their research has shown that climate change is decreasing forest biomass, and because it and the reason for that is it increases respiration at night. Of course, you know that trees breathe just like us. They respire at night because there's no sunlight, and that the increased nighttime temperature is causing an increase in nighttime respiration. Okay, climate change is raising sea level from the melting of land ice into the ocean, and then water expands when it warms. So two reasons for this. And here's an island off the coast of India, experienced sea level rise. The global average is about 20 centimeters. So, you know, maybe about halfway to your knee since pre-industrial. This is a national park in the heart of Washington, D.C., which has experienced sea level rise at twice the global rate. This is the tidal basin. It's part of the National Capital Parks. And this is where the cherry trees are, but you can see very clearly here the sea level rise right at our nation's capital. Climate change is bleaching corals. It's the heating of the water. The increased energy of climate change, 90% goes into the oceans. And so, of course, it's raising sea surface temperatures. And coral bleaching, the most serious places are the yellow dots here. And this is in the Great Barrier Reef, a key protected area for our planet in Australia. This is Cabrillo National Monument, and off the coast of San Diego, the University of California Scripps Institute of Oceanography has been monitoring ocean acidity, and we see an increase of ocean acidity of 12% since 1984, just off the coast of this national park in California. And the result of that is the corrosion of the shells of shellfish and the dissolution of corals. And so this is marine life in Papahanaumokuakea Marine National Monument off the coast of Hawaii, one of the largest protected areas in the world. Okay, so that was bad news, and it gets worse regrettably before it gets better. But I'll try to go through quickly. So that was detection and attribution of things that are already occurred. I'm going to show just a few examples of what might occur under continued climate change. And to do this, climate change scientists, we use projections of the future emissions scenarios that have been developed by the IPCC. And the black line here is observed temperature changes. And this is about the present going back. And then the colored lines are 5 different emission scenarios. And emission scenarios are storylines of the future that are a function of population, of energy use, and economic activity. So it's all a function of human behavior. And of course, the worst case is the darkest red here. And the best case is meeting the Paris Agreement goal. I'll talk a little bit more about that. And then we have these intermediate. So where do you think we are? Where does somebody think we are? Actually, Utah State, you have a lot of climate change scientists here, so I'm sure somebody knows exactly where we are. Which colored line? I'll just guess. Uh-huh. Okay. So actually you were all pretty close. We're actually we're between this red line and the orange line. So we're actually going in the right direction, but we actually need to be in the blue line, and I'll talk a little bit more about that later. Okay, so one of the projections is for potentially increased drought. So a drought that has a frequency currently of 1 in 100 years, potentially occurring every year in Arches National Park and across the Western United States. There's 3 different indices of drought here. And on the other extreme, an increase in the strongest category of hurricanes. Not an increase in the number of hurricanes, but an increase in the fraction of hurricanes that are category 4 and 5. So colleagues and I, we identified 5 key risks to ecosystems under climate change: biodiversity loss, structure change, that's like biome shifts, tree mortality, wildfire increase, carbon loss. So IPCC reports are full of these types of graphs, and we designed these to try and communicate to policymakers in just one glance, kind of the risk levels of taking action or not taking action. And so this is the temperature above pre-industrial, 0, 1, 2, 3, 4, 5 degrees. The gray bar is the present. And so we're at 1.2 here. And then the colors, if it's white, no impacts have been detected. If it's yellow, a few individual cases have been detected and attributed to anthropogenic climate change, like I showed you in that section. When it goes into the red, it isn't just, it goes from being individual cases to being more widespread, so regional. And then purple it's everywhere. And so we see here that the transition from white to yellow is we've passed that for all of these risks. And it's the transition from yellow to red occurs generally between 1.5 and 2 degrees Celsius. So this is the scientific basis for the international policy of a 1.5 to 2 degrees target under the Paris Agreement, because you see going from yellow to red here. That's where ecosystems really start getting hit. Okay, so the first major vulnerability, major risk is extinctions, including the extinction of this iwi bird, which is listed under the US Endangered Species Act as threatened specifically due to climate change, and potentially under 4 degrees Celsius could experience 13% extinction globally, and that would be equivalent, or it's even more than all the extinctions of plants and animals that have occurred in the past 12,000 years due to habitat destruction and hunting. So pretty serious risk. I mentioned the US Endangered Species Act. To my knowledge, my examination of the database, 33 species are listed by the United States as threatened specifically due to climate change, including the Canada lynx, pictured here in North Cascades National Park. Okay, so colleagues and I analyzed the potential risks of biome shifts, and I'm just going to zoom through this really quickly. So that's today, and this is under the worst case. So that's today under the worst case, and you see potential shifts of hundreds of kilometers. Oops, sorry. Perhaps 1/10 of global area. And if you include their habitat destruction, which erects barriers to dispersal, their vulnerability shoots way up to maybe half of terrestrial land area. Another vulnerability is tree mortality due to drought, including the tallest living beings on Earth, coast redwoods here in Redwood National Park, threatened by drought under climate change. And then a potential increase of wildfire, half to 3/4 of the terrestrial land area. And then the sea level rise could inundate parts of many small island nations, including the nation of Kiribati in the South Pacific. So, so the global average was here about halfway to your knee. Then Washington, D.C. was here, almost to your knee. And then under the worst case at the end of the century, 1 meter, so up to your waist. But that's a transient solution, actually. If you continue going, it doesn't peak at the end of the century. It actually could continue. Okay. Then more coral bleaching. So I'm going to zoom to the next and just briefly talk about adaptation and resilience. So just going to show a few slides here and some basic principles of adjusting natural resource management practices under climate change. And the first is integrating climate change into reference conditions. So a lot of vegetation restoration, fire management, other natural resource management practices, it aims towards some ideal condition, reference condition, but we can't return to a lot of the reference conditions of pre-European settlement. And so I'm going to talk a lot more about this tomorrow in the case of wildfire. Integrating climate change, so you're aiming towards a different reference condition under potential future conditions, is one key approach. Another is identifying refugia or potential stable areas under climate change. And then another approach is selecting plant seeds and other propagules that are under current climates adapted to hotter, more arid conditions, and using those for ecosystem restoration. Okay, so two examples. One here, Nicholas Graver and Joshua Tree National Park, where they've used the published research that identified potential refugia for the Joshua tree. And so the national park is very extensive, and they don't have enough money or staff to actually do everything everywhere in the park. So they're focusing in on these refugia, and they focus their fire control, their invasive species removal, and even here, their scientific monitoring of populations over time. This is a more effective use of resources. And that last point of the propagation here is just outside the National Park of American Samoa, where they've found local native corals that showed resistance to hotter sea surface temperature, and they're raising them in these underwater nurseries, and then they'll outplant those for more resilient coral reefs. Okay, so last 5 minutes, we'll go through solutions to all of this. And I mentioned the 1.5 to 2 degree goal. That's the Paris Agreement goal. And I'm actually going to talk about that policy just a little later. So 1.5 to 2 degrees, this is that. This is time. This is temperature here. So ideally, we're trying to get that. We're trying to follow that green line. Secondarily, we could follow these other two lines, but this would be great. To hit 1.5 requires us, these are emissions. This is temperature, and these are emissions. The 1.5 goal requires us to cut our carbon pollution, cut our carbon dioxide emissions to net zero by 2050. And if we relax the criterion, we have until 2090. But let's go with the 20.5 goal, the greatest ambition. Net zero means no gasoline-powered cars. It means no burning coal. It means no burning methane gas. It means replacing everything with solar, wind, other renewables, except for a small residual use of fossil fuels for essential plastics and some other globally essential uses. So, of course, that's a huge challenge, But we are starting to meet the challenge. Great. So this graph is just a couple decades here. And these are emissions on this side. And these colored lines show different pathways. And the black is historical emissions. And globally, we're leveling off now. If we implemented all national policies that are in place now, or actually, all national policies that are in place now, their implementation would get us to 3.1 degrees Celsius. Okay. Before the Paris Agreement, the national policies would have led to 3.7 to 4.8 degrees Celsius. So we've already come down. We were actually way up here. We're already coming down. And then under the Paris Agreement, all of the country pledges would get us to 2.6. So we're moving in the right direction. We're not exactly there. We still need a 42% cut of emissions to hit this net zero goal. And just more on the challenge here. China is the biggest emitter now in the world, but the United States is the biggest emitter per person. Okay, so the first solution is halting deforestation. That would cut global emissions 9%. Halting deforestation like here in the Congo rainforest, in Gabon. And of course, this would have great benefits for biodiversity conservation. But another major solution is becoming more efficient in transportation. So if all of the cars and light trucks in the United States were their own separate country, they would be the #7 carbon polluter in the world. Just the cars and trucks in the US emit more greenhouse gases than all of France and all of Canada combined, or all of Japan combined. Making transportation sustainable in the United States is an extremely important solution. And we actually have the technology and the behaviors right now. Walking, biking, public transit, you can take meaningful action on climate change individually by and cut your emissions by over 99%. I live a car-free life, and I encourage everybody to also. Almost all of my adult life, I've lived car-free. Next time you go to Salt Lake City Airport, hop on the Salt Lake Express. Don't drive. Here are actually the numbers behind that. Another meaningful personal action that you can take is a plant-rich, meat-free diet. I'm vegetarian and I do this. Global adoption would actually cut greenhouse gas emissions globally 40%. Remember, we're trying to cut it 100%. So this action actually gets us much of the way there, 40%. A lot of research, as you see, on this. Okay, these two actions are not easy. I know that, but I'm challenging you to actually maybe start by not driving 1 day a week, or maybe start by not eating meat 1 day a week, and then let it build from there. Okay, renewable energy. Now I'm going to start with a lot of the good news. So since 2000, the world, we've installed so much wind, solar, and other renewable energy, that we've increased renewables 600%, equivalent to 9,000 coal-fired plants. So since 2000, enough renewable energy that we've avoided needing 9,000 coal-fired plants. And that, of course, is, anyway, that's a huge advance. And so from renewable energy and other sustainable practices of public transit and other sustainability practices, the European Union has cut its emissions 1/3. And in the United States, renewables actually exceed coal for the first time since the 1880s. And that's because wind and solar and other renewables are now cheaper than methane gas, than coal, than oil, and nuclear. And of course, they're cleaner and better for the environment and better for human health. Okay. So in the United States, we've cut our emissions 20% since 2005, including with this solar panel in Lassen Volcanic National Park. And a lot of that has been driven by forward-looking policies. President Obama started with the regulation of greenhouse gases through a scientific declaration of the endangerment of human health and welfare due to anthropogenic climate change. The US government is able to regulate greenhouse gases under the Clean Air Act. And then President Obama started with this massive investment with renewable energy that we see today. And then President Biden here, of course, enacted 2 major pieces of legislation for jobs, for reducing inflation, and for taking action on climate change, the biggest government investment in cutting greenhouse gases. So obviously, I need to recognize the backtracking that has occurred since then. Of course, the current administration is attacking science, is blocking science-based action on climate change, on environmental quality, on human health, on democracy, a lot of things. We're going to stick with climate change here. A lot of this investment actually went out already before the current administration. And investments in renewables are long-term. So during the first time they were in office, the investments of President Obama carried through for 4 years, and we continued to cut our emissions. And so they're going to be gone in 3 years, and after that we'll rebuild and continue our progress. And join the community of nations. 191 out of 194 independent countries in the world agreed to the Paris Agreement. And that means almost every country has agreed voluntarily to cut their greenhouse gas emissions to meet that 1.5 to 2 degree limit. And this was the formal signing at the United Nations in New York. And in conclusion, I wanted to point out again a major conclusion of the Intergovernmental Panel on Climate Change is that with existing technology and behaviors and concerted global action at all levels, governments, corporations, and individuals, we can technically meet that 1.5 to 2 degree Celsius limit through sustainability actions of, again, individuals, corporations, and governments that exist today. So you and me and all of us together, we can halt climate change. The science shows it. Policies are there. Recent progress shows that we can halt climate change. and protect people and nature. Thank you. So thank you very much for your interest. That I know we're right at time, but if you have time and want to ask questions, I'll be happy to answer questions, unless you have some policy that everybody has. Yeah. Sorry, I went up exactly to the end of the hour, but yes, questions. Yes, in the back with the hat. Yep.
But I was thinking about the Paris Agreement. And so with climate change policy, I feel like economic factors also put up a major roadblock. Because if you have like two different countries, right, and one independently decides to put in place a lot of these like climate forward carbon reducing policy, and the rest of the countries do not, and that responsible country is at least in a short term big economic disadvantage. So for those reasons, like agreements like the Paris Agreement are super important because we're having all countries or almost all countries agree to like not impose this economic advantage on one country or some countries, but all take on that burden so that the playing field is still level, say economically. However, when we have countries like the United States that seems to waffle on whether or not we'll be signatories to this agreement based on which political party holds the White House, how can we have faith that these agreements will actually be effective in the long term? What's to stop, like, say, Russia or China or France or England from having a new party take hold? Like, we don't want to do anything.
Thank you. I pointed out how we've actually achieved some success with the Paris Agreement. IPCC, the estimate of the temperature increase, we've gone from 3.7 to 4.8 degrees. After the Paris Agreement, down to 3.1, potentially 2.6. So the Paris Agreement has started to work, but you're correct in that the weakness of the agreement is that it's voluntary. It's a strength and it's a weakness. It's a strength because the previous agreement, which was called the Kyoto Protocol, actually was mandatory. And so it only applied to the industrialized countries in the world. They didn't want to force all of the countries to do it because, as you're saying, because economic disparities. So the voluntary aspect was a way to get everybody on board. So it's a strength, but it's a weakness because, as we've seen, a country, well, regrettably, the United States, it's the only country that has withdrawn, ever withdrawn from the agreement. So what are the prospects going forward is what you're saying. You started off talking about economics, and actually economics are pushing this a lot. As I said, a lot of the renewable revolution has been because of the economy of scale, reducing the per kilowatt cost, per kilowatt hour cost of marginal, adding another, capacity. And we actually have to look to China right now, which has a booming, it's very interesting because they're the number one emitter, but they're also the number one producer of renewable energy technology, and they're actually selling their technology, making, well, they're making a lot of money off of it. And they're actually powering about half of the economic growth from renewables right now. The share of renewables as their total energy has really shot up. So there's a few thoughts. Perhaps one more question, or yes.
I have seen some reports that related the higher economic incomes with the higher gas emissions are. So I wonder if the IPCC integrates that information, like in the reports or the advices provided, the measurements that advise to the government, is there something related to climate justice, iterate in the report or in the fiction that?
Yes, thank you. You're asking a question with a lot of different pieces, and so I'll try to summarize. So on your first point, it is let's think of the eventual emissions in three parts. And this is my PhD advisor developed this concept actually, and actually he was a great inspiration. His name was John Holdren, and he actually served as science advisor for President Obama. Anyway, he developed an equation, the IPAD equation: population, affluence, and technology. So population, people; affluence, dollars per person; and then technology, the emissions per dollar. So the emissions per dollar is a form of efficiency. So the fewer emissions that you have per dollar of economic product, the more efficient you are. The middle is also a form of efficiency, dollars per person, and then there's the people. So it is true that higher income countries actually are less efficient. But that's been improving over time, especially in the United States. A lot of our reduction in emissions comes from increased efficiency, so fewer emissions per dollar of economic product. But now you're asking, in the IPCC and in the in the research and practice in general, this issue of equity globally, been trying to encourage leapfrogging dirty industries, much like cell phone technology leapfrogged copper wire. So solar leapfrogging coal and methane gas. A country that is not high income actually can, through the use of renewables, actually avoid a lot of the environmental damage, and it costs less, and it improves independence because you don't require imports. Anyway, that's one approach to address what you're saying about equity. Renewables actually answer a lot of questions for us, and so it's an important solution for climate change and biodiversity and for human well-being. Thanks for listening to me talk on, and I guess we're going to be eating food. Thanks. Thanks. Great. I'm going to log out. Stop sharing.